Hey everyone, this is a lesson for section 3.1. Had a lot of absences, so I decided to make a quick video. I may be going what seems like quickly, so as always, feel free to pause the video and catch up if you need to. So we are talking in all of Chapter 3 about exponential functions. So these are our learning targets. We're going to evaluate exponential functions with the base e. So this is an exponential function where the base is a number and your variable is an exponent. That's why it's called an exponential function. So we're going to look at ones with base e. We're going to base a, where a is a number. So for example, 2 to the x. We're going to look at with a base e, and then we're going to look at solving some problems. So again, this is all exponential functions. So this kind of gives you an overview. This is what you're going to want to put in your notes. The exponential function f with base a is denoted as this. Let me zoom this in a little. So a to the x, and then this is an example where your base, you call this big number. Your base is 2, your exponent is your variable. So this says a must be greater than 0, so that means this base must be positive, and it cannot equal 1. And x can be any number. The reason it can't equal 1 is because if you think about it, 1 to the anything, 1 to the 2 is 1. 1 to the 3 is 1. 1 to the 4 is 1. So that's just the constant function f of x equals 1 or y equals 1. So that's not really an exponential. So that's why we say a must be greater than 0, which would mean it's positive, and a cannot equal 1. So they're going to look like this: 2 to the x, 3 to the x, 4 to the x. They could be a decimal, 2.1 to the x. And they actually could be a fraction. All right. So the first thing you want to double check is make sure you can put these into your calculator. So this is the function. We're substituting in the value, negative 3.1. And so this is your calculator step. So 2, I'm just going to show you actually on my calculator. This is how you're going to do your exponent. And then it's maybe not quite so important on the 84, but on the 83 for sure. Notice how I have that wrapped up in parentheses. You're going to want to put it in parentheses. Now, I have an 84, and you can see that it didn't make a difference. But I always just put, if my exponent is, say, more than one thing or a fraction, I wrap it up in parentheses. So practice a couple of these. And these are the answers you should get. So 2 to the power of negative 3.1, you should get that. 2 to the negative pi, you should get that. 0.6 to the 1.5 or 3 over 2, you should get that. So again, pause the video, practice punching these in your calculator, make sure you're getting the right answers. So when you go to do your homework, you get those correct. This was a U-try that we did in class. So this is x's square root of 2. So you're going to have this 8 to the negative square root of 2. And that's going to be f of square root of 2 equals that. So I'm replacing x with the square root of 2. And you should get that. So again, pause the video and check those. Okay, we are going to look at graphs of exponentials next. I'm just going to go right down to this. So the first two that we're looking at are 2 to the x and 4 to the x. So they have a table of values here, but I just want to go through how we would create this table of values. There's a couple things you want to notice for sure, that when x is 0 for both of these graphs, y is 1. As x gets bigger, y is getting bigger for both of these. That's because they are growth. When x gets bigger, y gets bigger, and these functions are headed rapidly to positive infinity. So we call these growth when your graph is headed up toward positive infinity. Now I just wanted to, I'm just going to do this for one. I want to do a quick table of values here. So I'm going to do those same 5 numbers we always like to check. -2, -1, 0, 1, 2. So this is going to be 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 1, and 2 squared. Now these are pretty easy, right? 2 to the first power is 2. 2 to the second power is 4. So that's going to be the coordinate point over 1 up 2 over 2 up 4. This point that I talked about down here, anything to the 0 power is always 1. So that's why these two different graphs, 2 to the x and 4 to the x, have the same y-intercept, and you can see it here on the graph. That's going to be true for any of these. 5 to the x, 6 to the x, 7 to the x, they're all going to have the same y-intercept, because when x is 0, doesn't matter what your base is, anything to the 0 power is 1. Now these, we need to do a little refresher of what happens with negative exponents. So I don't have a lot of room there. I'm actually going to do it over here. So when you have a negative exponent, you may have forgotten this. I don't think they reviewed this again in Algebra 2. But what you want to do is take the reciprocal of your fraction. Or I like to say this base with this exponent is unhappy upstairs, so send it downstairs and it becomes happy. So the negative exponent becomes positive. So then this would be 1 over 4. So then this would be 1 over 4. So when x is -2, y is 1/4. 2 to the -1 would be 1 over 2 to the +1, which would be 1/2. So that's where these fractions are coming from. 2 to the -3 would be 1 over 2 to the 3rd, which is 1/8. So as we're headed to the left here, as x approaches negative infinity, both of these graphs are getting closer and closer to the x-axis, or the line y equals 0. So these have a horizontal asymptote at y equals 0. Again, pause the video if this is going too quickly. This is kind of just a summary. It says attach them by connecting them with a smooth curve. Do a quick table of values. Functions like this you would be expected to do without a calculator, because you can easily do that table of values like I just did. And then, you can always also put it in your calculator. You would do y equals 4 to the x, y equals 2 to the x, and then you could always do your table to see all your coordinate points. Okay, a little more on graphs. This is what we already talked about. The base needs to be positive and it cannot equal 1, reminding you that the variable is an exponent. That's why they're called exponential functions. And then they're just saying, hey, many real life phenomenon follow this kind of pattern of growth. When we started COVID, whatever, year and a half ago, they talked a lot about it growing exponentially. Actually, it didn't grow exponentially because it eventually leveled off. So this you're going to want to put in your notes. And this side I would label growth. And this side I would label decay. So the domain and range are going to be all real numbers, because if you think about those graphs that we just looked at, let me put it back for a second, these graphs are going to the right and left forever. So my x values, there's no discontinuities, no holes, no vertical asymptotes. So domain is all real numbers. The range for these parent functions, ones that we haven't translated around, again, the smallest y value is not 0, because y equals 0 is a horizontal asymptote, and then it goes up forever. So we didn't include 0. but we said the y values are anything above 0 to infinity. The y-intercept, this is actually the y-intercept, 0, 1. Remember, they were the same for both of those functions. And the growth is increasing always, and the decay is decreasing always. Now for decay, I just wanted to put an example. So this book is going to tell you if you have that, that is decay. So if your exponent is negative. Now I'm going to use that negative exponent rule that we just did, and I'm going to say, hey, that's equal to that. And then I'm going to say, hey, that is equal to this, because 1 to the x is always going to be 1, and then 2 to the x on the bottom. Notice this number is what I'm referring to right here. I'm saying also your decay might look like this. If your base is greater than 0 or less than 1. So I call these the measuring cup fractions, because they are the fractions you see on the measuring cup. And if you think, a measuring cup goes from 0 to 1. So your base might also look like this. That would also be decay. A negative exponent or a base that's a measuring cup fraction will be decay. Domain, again, is still going to be all real numbers. Range is going to be from 0 up. Y-intercept is going to be 0, 1. But this one is always decreasing. This is decay. So these are what the graphs looks like. This is growth. This is decay. So for the growth function, as x approaches negative infinity, so that's over here, your function approaches 0. Or a to the x, which is our function, approaches 0. Over here, as x approaches positive infinity, this one is decay, this one is growth. So here, as x gets bigger and bigger, that's when my function approaches 0, or a to the negative x approaches 0. So decay is down and to the right, growth is up and to the right. So again, put these in your notes. They're continuous, no vertical asymptotes, no holes. You can draw these graphs without lifting your pencil. So this was just a little practice we did of punching this in your calculator and sketching it. Now the base is 3, so a equals 3. Your exponent is negative, so that's going to be decay. So then your function should go down and to the right, which is exactly what you have when you graph this. This one is 9 to the negative x. This is actually your 3 to the negative x. So approaching 0 as x gets bigger and bigger. All right, these next few examples, we are looking at transformations. Okay, so think of this as your parent function, and this is a transformation. Now, this plus 1 is up there. Think of it as on the inside, right? When we did quadratics and it was on the inside, looked something like that. Think of this as on the inside. So this is a horizontal translation. And remember, those are the ones that do the opposite. So we're going to go 1 to the left. So this is my 3 to the x. 3 to the x has a y-intercept of 0, 1. I'm going to take that 1 to the left. So this point is going to be at negative 1, 1. The other point I like to check is when x is 0. So if x is 0, I would have 3 to the 0 plus 1, which would be 3 to the 1, or 3. So you can see my y-intercept actually moves up here to 0, 3. So that is a 1 to the left. I'm going to do these next two quickly because you might have just heard that a bell rang. So here's the transformation we're doing on this graph. This is going to be vertical, and this is going to be down 2. So when the number is hanging off the end, I like to say, not included up here in your exponent, those are the easy ones. This is my 3 to the x. The y-intercept was at 1, so I'm going to move it down 2. So my y-intercept is now at 0, -1, and then sketch my graph. Again, if you want to do a couple other points, you can do a table of values. This one is going to be a reflection. The negative in front, remember that's a reflection over the x-axis. Now the thing you have to be careful of on this one, I'm going to resketch this. So this is 0, 1. So this is 3 to the x. Now it doesn't touch the x-axis, so you have to think I'm reflecting over the x-axis. So this point is 1 up from the x-axis. When I flip it over, it's going to be 1 down from the x-axis. So that's going to be at 0, -1, and then the whole graph is also going to flip. So you'll notice the y-intercept goes from 0, 1 to 0, -1 because you're reflecting over this x-axis. So hops all the way down there. I'm going to stop this and do the next part in another video.